In this episode, we will talk about BIELIK 11B V2 Technical Report. We're taking a deep dive into the technical report of BIELIK 11B V2. Now, this is an advanced language model, and it's specifically designed, really fine-tuned for understanding and generating Polish text.
That's right. And what's quite interesting here is that it builds on a really solid foundation, the Mistral 7B VV0.2 architecture.
Okay, Mistral 7B. Yep.
And this is the key part. They use something called depth upscaling. They significantly increased its capacity up to 11 billion parameters. That's quite a jump.
11 billion, wow. So it's scaled up significantly.
Exactly. And this bigger scale lets BIELIK 11B V2 get some, well, really impressive results across a whole range of Polish language benchmarks. But it's not just Polish. It actually shows pretty strong capabilities in other languages, too.
Okay.
Today, though, we really want to dig into how it works. We'll focus on two key technical innovations the BIELIK team introduced: weighted instruction cross-entropy loss and an adaptive learning rate.
Weighted instruction cross-entropy loss
Right.
and adaptive learning rate.
Yeah, these seem to be really central to its improved performance. Kind of the secret sauce, if you will.
Okay, let's unpack this then. These sound like the core advancements that really make BIELIK stand out. So our goal today is to go through this technical report, pull out the really crucial insights. We'll look at, well, everything: the basic design, the architecture, all the layers and how they connect, and also the very careful process they use to prepare the huge data sets for training.
And the training itself, how they measured its success, the evaluations.
Right, the evaluations across different tasks,
Hmm.
and even how you can compress it or quantize it so it runs on different kinds of computers. We really want to make these complex technical ideas understandable, almost like explaining it to a curious non-computer science professor at Yale, someone smart but not necessarily deep in the CS weeds.
Exactly. We'll break down the essential parts, explain the tech concepts clearly, hopefully in an enlightening way. We've got the technical report right here as our guide, so we'll stick closely to what the researchers found to really understand what makes BIELIK 11B V2 tick and why it's making waves in Polish language AI.
All right, let's start at the beginning, the architecture. The report says clearly, BIELIK 11B V2 is built on the transformer architecture.
Which pretty much the standard now, yeah.
For anyone maybe not super familiar, the transformer is, well, fundamental in modern natural language processing. Its real strength is figuring out relationships between words, even if they're far apart in the text. Now, the report has this detailed table, Table 1, packed with key parameters. Can you walk us through some of these? I see things like 50 layers, a model dimension of 4096, 32 attention heads. What do these numbers actually mean?
Sure. So the transformer relies heavily on this mechanism called self-attention. That lets the model weigh how important different words are when it's processing text. The numbers you mentioned give us a sense of the model's size and complexity. 50 layers. That's a deep network. It can learn really complex patterns.
Yeah.
The model dimension, 49.6, that's like the size of the internal thoughts or representations the model uses for words and their connections. Think of it as the richness of its understanding at each step.
Mm-hmm.
And 32 attention heads. That means the model can look at different parts or different aspects of the input text all at the same time, like having, 32 readers analyzing the text in parallel, each focusing on something slightly different. It gives a more complete picture.
Multiple perspectives on the text simultaneously. Okay, that makes sense. More detailed analysis. The table also mentions causal masks with this self-attention.
Yeah.
What do the masks do specifically?
The causal mask. That's absolutely critical for making the language model generate text realistically, one word after another. It basically limits what the model can see. When it's predicting the next word, the causal mask stops it from peeking ahead at the words that actually come later in the sequence.
Right, it can't cheat.
Exactly. It can only look at the words it's already generated. This is essential for keeping the generated language flowing coherently, just like how we speak or write.
Got it. Prevents predicting based on future information, ensures a natural flow. Now, another term here is grouped query attention, or GQA. The report says this reduces computational needs and memory use. How does GQA manage that?
Right. Grouped query attention, GQA, it's a smart optimization of the standard multi-head attention we just talked about. In the regular setup, each of those attention heads has its own separate set of weights for queries, keys, and values.
Mm-hmm.
GQA, well, it reduces the number of key and value head compared to the query heads.
Yeah.
So what happens is several query heads end up sharing the same key and value calculations. The model can still attend to different things because it has multiple query heads, but it does it with way less computation and uses less memory, especially with really long texts. It's a clever trade-off, get most of the benefit with less cost.
That sounds very practical, making the model more efficient without really hurting its understanding too much. The activation function they used is SwiGLU, not the more common RealU. What's the advantage of SwiGLU?
SwiGLU, yeah, it's a mix of swish and gated linear units. Research has shown it can actually lead to better performance and more stable training compared to RealU, the rectified linear unit.
Which is simpler, right?
Much simpler. SwiGLU has this gating mechanism, like a little switch, controlling the information flow inside the network. This kind of finer control helps the model learn more complex patterns and generally makes the training smoother and more effective.
It's interesting. A more refined way for the neurons to decide when to fire, basically. The report also mentions rotary positional embeddings, or ROPE. How do these help the model understand the language structure?
ROPE, yeah. Rotary positional embeddings. It's a way to encode where each word or token is in the sequence. Unlike older methods that just assigned a fixed code for each position, ROPEs uses rotation to encode relative positions.
Relative positions.
Exactly, which have a couple of big benefits. One, it helps the model generalize better to text sequences that are longer than what it saw during training. Two, it improves performance on tasks where the exact order and relative placement of words is really important for meaning, which is, well, most of natural language. It's not just that a word is there, but where it is compared to others.
So it captures the word's position relative to its neighbors, not just its absolute spot, crucial for nuance. We also see root mean square layer normalization, or RMS norm. What's its job?
RMS norm. Root means square layer normalization.
Yeah.
It's a technique to stabilize and speed up training deep networks. It normalizes the activations, the outputs of the neurons within each layer.
Okay.
This stops the activations from getting too big or too small, which can mess up training. RMS norm is basically a more computationally efficient version of the standard layer normalization. Gives you similar benefits, stability, speed, but with a bit less computational overhead.
Efficiency again. Seems like a running theme. The report also mentions pre-normalization. How's that different from RMS norm, and what's its effect?
Pre-normalization is about where you put the normalization step, in this case, RMS norm, within the transformer block. Instead of normalizing after the self-attention and feed-forward layers, you do it before.
Seems like a small change.
It does, but studies show it can actually make a big difference in how well and how fast the model learns. It often leads to better convergence, meaning the model settles on good parameters more reliably and potentially better final performance.
Subtle, but important for training. Now about scaling up. BIELIK 11B v2 was scaled using the depth upscaling method from Mistral 7B's 32 layers to 50. Figure 1 shows this. Can you explain how depth upscaling works here and why they landed on 50 layers?
Sure. Depth upscaling here meant taking a smaller, good model, Mistral 7B v.2 with 32 layers, and making it deeper, adding more layers to get a bigger model with more capacity. As Figure 1 shows, they basically took a chunk of layers from the middle of Mistral specifically, 7 layers, and just repeated that block. Then they tweaked the layers at the start and end to hit exactly 50 layers total.
Okay, so they duplicated some middle layers. Why 50 specifically?
The main reason for 50 layers was to get the model size to around 11 billion parameters. This was strategic. It's a big jump in capacity from 7 billion, letting it learn more complex stuff in Polish. But crucially, 11 billion parameters is still runnable on, let's say, higher-end consumer GPUs, graphics cards with up to 24 gigs of VRAM.
Ah, so it's powerful but still somewhat accessible.
Exactly. Makes it usable for researchers or developers who don't have access to giant supercomputers. It balances power and practicality.
That makes sense. A calculated trade-off. The report also stresses the strategic choice to build on Mistral 7B 0.2. Why not just start from scratch?
Oh, building on Mistral 7B v0.2 saved a huge amount of resources. That model is already pre-trained on tons of general text. It already had strong language skills.
Right.
By using that as a base, the BIELIK team could pour their resources, time, compute power into the really important part, adapting and training it specifically for Polish. They didn't have to do the massive, expensive job of training an 11B model from zero.
Plus the license, I assume.
Good point. Mistral 7D v0.2 has the Apache 2.0 license, which is very permissive. That made it legally straightforward for them to build on top of it.
Makes perfect sense. Start with a good engine, then customize the car for Polish roads, rather than building the engine piece by piece. Lastly, on architecture, the tokenizer. They mostly kept Mistral's tokenizer, but added a few special tokens. Why that approach?
Right, the tokenizer breaks text into pieces, tokens, the model understands. Mistral's tokenizer, with 32,000 tokens, was already pretty good at handling diverse text. Sticking with it meant they could leverage its existing strengths and the fact the original Mistral layers were already tuned for these tokens.
Okay.
They just added a handful of special tokens, bringing the total of 32,128, mainly for formatting things like chat interactions or instructions, tokens to mark who's speaking or the start end of an instruction. Minor additions for specific needs.
Okay. That wraps up the architecture nicely. Let's move to pre-training. The main goal here, the report says, was boosting the model's Polish skills, accuracy, and fluency. They used a huge, diverse set of high-quality Polish texts. Tell us about this data.
Absolutely. The pre-training data was key. It was mostly Polish text, sourced heavily from the SwiGLU project. Yeah, it's an initiative focused on creating large language datasets. They selected 41 million documents from SwiGLU using metadata like topic and stylometric features, measures of writing style, to ensure high quality and broad coverage of topics and styles in Polish. These 41 million documents then went through some serious cleaning and quality checks.
41 million is massive, and I noticed they mentioned excluding documents based on terms and conditions about training language models. That feels pretty important ethically right now.
Very important. You can technically scrape data, but respecting usage terms is crucial, legally and ethically. The BIELIK team was careful to exclude any documents that prohibited use for model training. After all that filtering and cleaning, they ended up with a Polish training corpus of 90 billion tokens.
90 billion tokens? That's just staggering. But it wasn't all Polish, right? They included some English text from Slimpajama. Why bring English into it?
Good question. Adding English text from Slimpajama served a couple of key purposes. First, it helps the model keep and maybe even improve its general cross-lingual abilities understanding languages besides Polish. Second, it helps fight against something called catastrophic forgetting.
Ah, right, where it forgets what it knew before.
Exactly. When you train intensely on new data, like Polish here, the model can start losing the knowledge it gained from its initial training. Mixing in some English helps it hold on to that broader language understanding, preventing it from becoming only a Polish model.
Keeps it grounded. Makes sense. They also mentioned mixing in the instruction data set, the one meant for post-training, into this pre-training phase. Why do that?
That was a strategic move. It helps smooth the transition to the later fine-tuning stages. By showing the model instruction-like data early on, it starts learning the basic pattern. Here's a prompt, here's a desired kind of answer.
It's like a preview.
Sort of. It makes the later specific instruction following training more effective because the model already has a foundational grasp of the concept. It's not starting completely cold on instructions later.
Give it a head start on understanding instructions before drilling down. Okay, so what was the grand total size of this final pre-training data set, Polish and English combined?
The final pre-training set was enormous, 198 billion tokens across 96 million documents. That huge amount of diverse, high-quality data is what gave BIELIK v2 its strong language foundation, especially in Polish.
198 billion tokens. Wow. Okay, let's get into how they prepared this mountain of data, the data cleanup process. What kind of automated rules, these heuristics, did they use?
The cleanup used a whole suite of automated checks. They looked for and removed corrupted or irrelevant stuff like garbled text or maybe machine-generated noise. A really critical part was anonymizing personal data. Finding and removing things like addresses, emails, phone numbers, URLs. That's vital for privacy.
Yeah.
And finally, they tackled technical glitches, fixing encoding problems, formatting errors, just making sure the text was clean, consistent, and ready for tokenization.
So a multi-pronged effort to scrub the data quality, relevance, privacy. Then, after cleanup, they did this extensive quality evaluation, manually labeling documents as high H, medium, or low quality. Why was that manual effort so crucial?
Manual annotation is key for building a quality data set. It lets the researchers define precisely what they mean by high H, medium, low quality for their specific goals. This human judgment creates a ground truth, a gold standard, that they can use to train and test automated quality assessment tools. It also helps them understand what makes text high or low quality so they can refine their filters.
And they really ramped up this effort for BIELIK v2, didn't they?
They did. Significantly larger annotated set for v2. 20,000 training samples, 1,500 tests, 500 validation. This bigger set let them train a more reliable quality classification model. For each document they annotated, they extracted 150 stylometric features.
Right, you mentioned stylometrics. And for v2, they focused heavily on features related to markdown formatting. That's interesting, like counting bullet points, links, code blocks. even analyzing table formatting.
Exactly. Since Markdown is everywhere, online tech docs, forums, wikis, these features gave them a much better handle on quality in those contexts. They use a tool called stylometrics as inspiration. Ultimately, they found an XGBoost classifier that's a type of machine learning model worked best for telling the quality categories apart based on these 150 features.
The report even ranks the most important features using something called mean absolute SHAT values. Sounds complex. What did that tell them?
SHAP values shapely additive explanations basically tell you how much each feature contributed to the model's prediction. So the mean absolute SHAP value shows, on average, how much impact each stylometric feature had on predicting high GH, medium, or low quality. Table 5 shows this ranking. Things like the frequency of rare words, the percentage of non-alphabetic characters, the ratio of common stop words, those turned out to be strong indicators of text quality.
Identifying the key style signals for quality. How well did this quality model actually perform?
It did really well. On the validation set, 86% accuracy, 0.79 macro F1 score. On the separate test set, even better. 94% accuracy and 0.85 macro F1. That shows it was pretty good at distinguishing quality levels, especially finding the high-quality stuff. Figure 2 has the confusion matrices, showing visually where it did well and where it occasionally got confused.
Very strong numbers. And based on this, they set a specific threshold for including texts in the final pre-training set.
Yes, they manually checked the 1,000 documents and their model's predictions. Based on that, they decided that if the model predicted a document was high GH quality with over 90% probability, that was a reliable threshold. Anything below that 90% mark for high GH quality got excluded. It ensured only the best stuff went into the pre-training mix.
A very data-driven approach to curation. Now, another interesting bit was category classification. They built a classifier to automatically label Polish documents into one of 120 thematic categories. Why do that?
That category classifier was super useful by automatically tagging each document with one of 120 topics. Figure 3 shows the distribution. They could understand the thematic makeup of their huge data set and ensure it was diverse. But more importantly, it played a big role later in post-training. They used it to help create balanced instruction data sets, making sure the model saw instructions covering a wide range of topics.
120 categories is very specific. How did they build this classifier?
They trained it on about 36,000 Polish documents, split 90-10 for training testing, making sure categories are represented fairly in both sets. The process involved a few steps. First, count vectorizer to turn text into numbers based on word counts, focusing on the top 10,000 words. Then, TF-IDF transformation term frequency inverse document frequency, which highlights words important to a specific document compared to the whole dataset. Finally, they trained a linear support vector classifier, linear SVC, on those TF-IDF features. They also used something called calibrated classifier CV to get reliable probability scores for each category.
And how well did it work, assigning those 120 labels?
Pretty accurately. It got 94.44% overall accuracy on the test set, which is quite high. Table 6 has the details. The report notes most errors happened between closely related topics, which wasn't a major issue for their needs.
So, a very effective tool for organizing the data and also for building diverse instruction sets later. Okay, let's switch to the training hyperparameters for the pre-training stage. What were the key settings here?
Right, the settings. For pre-training, they used the AtomW optimizer, very standard, very effective.
Yeah.
Specific parameters, beta 1, 0.9, beta 2, 0.95, wheat decay 0.1. The learning rate followed a cosine decay schedule. It started higher at 2E5 and gradually dropped to 9E6 over the training run, with a short 50-iteration warm-up at the beginning.
Okay.
The whole pre-training took 97,250 iterations. They used Megatron LM, a framework for training huge models with a global batch size of 128. They also used tensor parallelism of 4, splitting the model across 4 GPUs, plus gradient clipping at 1.0 to keep things stable, and mixed precision training with bfloat 16 for speed.
And how much data did it see?
It was trained on the full 198 billion tokens over 2 full passes, or epochs, and with a really long maximum context length, 32,768 tokens. That lets it learn from very long pieces of text.
That's a lot of detail, but it shows a really carefully planned training run using advanced techniques for stability and efficiency. The report also mentions training process monitoring. How did they keep tabs on how well the training was going?
Constant monitoring is crucial for these big models. They tracked performance on the OpenLLM PL benchmark for Polish and OpenLLM EN for English throughout pre-training. They save checkpoint snapshots of the model regularly, and then they'd test these checkpoints on those benchmarks.
What were they looking for?
Well, if performance started consistently dropping on the benchmarks, that usually meant something was wrong with the data or the training process, and it was hard to recover from. To catch problems early and save compute time, they ran these benchmark evaluations on separate machines in parallel with the main training. That way, they didn't have to wait for a whole epoch to finish to see if something was going off the rails. Much more efficient.
That parallel monitoring sounds essential for such a massive job. Okay, after pre-training comes post-training. The goal here was to boost performance in specific areas: coding, math, reasoning, and following instructions. What did this involve?
Right, post-training takes the general language skills learned earlier and sharpens them for more specific, often harder tasks. This meant more training, but with different specialized data sets and techniques.
And the data is usually the first step. What data sets did they use for this phase?
This was a big effort. They found there weren't enough large, open, high-quality instruction and dialogue data sets specifically for Polish, so they built their own proprietary one.
Build their own, wow.
Yes, and they're continuously expanding and refining it with human annotators. People manually create instructions and dialogues across many topics. To boost the volume, they also used a large model, Mistral 8x22B, to generate more instructions and dialogues synthetically. This combo resulted in over 20 million instructions and about 10 billion tokens. Figures 4 and 5 show how these instructions break down by category.
20 million instructions.
And for the reinforcement learning part, aligning the model with user preferences, they created a specific data set of 72,000 preference instructions. These are designed to teach the model the difference between good and not so good responses.
That's a serious commitment to building Polish instruction data. The report then outlines this complex instruction data generation pipeline for alignment training. 7 steps. Can you give us the highlights?
It's quite meticulous. Step 1, instruction creation, humans writing instructions plus translating and tweaking English ones. Step 2, instruction deduplication, using tech like locality-sensitive hashing to weed out duplicates. Step 3, generation of chosen and rejected response pairs. This is key for preference tuning. For each instruction, they created a good chosen response and a less good rejected one, using both humans and other models like Mistral and Llama.
Okay, chosen rejected pairs.
Step 4, quality evaluation with metamodels. They use big models like Llama 70B and Mistral 8x22B to automatically score these response pairs on things like accuracy, clarity, reasoning depth, usually on a 0-10 scale. Step 5, filtering. They threw out pairs that had identical scores or where the scores were too close, or if the rejected response somehow scored higher than the chosen one. Strict quality control. Step 6, dataset cleaning, fixing formatting, removing errors. Step 7, manual inspection and correction. Humans double-checking samples, correcting things, adjusting scores for final reliability. And they emphasized the main goal here was aligning on style, dialogue, format, math presentation, storytelling, not primarily safety filtering.
An incredibly thorough pipeline with lots of human checks. Okay, after data prep comes supervised fine-tuning, or SFT. They made several improvements here to handle any remaining lower quality instructions. What were those?
Right, making SFT more robust. One technique was masked tokens. When calculating the training loss, the error signal, they only considered the tokens in the model's generated response. They ignored, or masked, the loss on the original user instruction and any control tokens. This focuses learning on generating good output.
Okay, focus the learning.
Another was the adaptive learning rate, ALR. We mentioned this earlier. It dynamically adjusts the learning rate based on how many tokens are in the current batch. The idea is to give each instruction, long or short, a more consistent influence on the training.
And the third one?
The third, and maybe the most impactful, was weighted instruction cross-entropy loss, or WISEL. This assigns a weight to each training example based on its quality score. Higher quality instructions get a bigger weight, influencing the model more. Lower quality ones have less impact.
So ALR and WISEL are the 2 big innovations we flagged at the start. Equation 1 in the report shows ALR scaling the learning rate, and equation 2 shows WISEL multiplying the loss by the quality weight.
Exactly. These were key to making SFT work well with a large, potentially noisy instruction data set. Prioritize the good stuff, adapt the learning step size.
What about the specific supervised fine-tuning hyperparameters? Were they different from pre-training?
Yes, they tweaked things for SFT, still AtomW optimizer, but slightly different weight decay, 0.05. The learning rate still used cosine decay, but started lower, 76, and went down to 6 C7, with the same 50 warm-up steps. Global batch size was 128, gradient clipping 1.0, still used BIELIK 16 mixed precision. A key addition here was sample packing.
Sample packing.
Yeah, they'd concatenate multiple short instruction response pairs together into one longer sequence, up to the context limit. It makes training more efficient by packing more useful data into each batch. SFT ran for 3 epochs with a context length of 8,192 tokens.
So tweaked optimizer, sample packing, different learning rate schedule, and context length. Okay.
Yeah.
After SFT, they discuss reinforcement learning. They tried a few techniques but landed on DPO positive, or DPOP. Why that one?
They explored several RL methods, standard direct preference optimization, DPO, proximal policy optimization, PPO, even others like KTO or RPO, SIMPO. They even built a Polish reward model for PPO. But their tests showed PPO, even with the custom reward model, didn't beat DPO. They ended up choosing DPO positive, or DPOP, because it fixes a potential issue with standard DPO.
What issue?
Standard DPO makes the model prefer the chosen response over the rejected one. But sometimes, in doing so, it might actually make the chosen response less likely overall, especially if the quality difference isn't huge. DPOP adds an extra penalty term to the loss function. This penalty discourages the model from reducing the probability of the preferred response compared to a baseline reference model. So it learns not just to prefer the good response, but to keep it likely. Equations 3 and 4 show the standard DPO loss and the DPOP loss with that extra term.
Ah, that's clever. Don't just pick the better one. Make sure the better one stays a strong option. What were the DPO positive hyperparameters?
For DPOP, specific loss parameters. Beta was 0.05, lambda was 2.5. These control the strength, the preference learning, and the penalty term. Still Atom W optimizer, but no weight decay this time. Learning rate was constant at 77 after the 50 warm-up steps. Global batch size 64, gradient clipping 1.0, B float 16 precision. This ran for 300 iterations total.
More tweaks. No weight decay, constant learning rate for DPOP. The report also mentions model merging. They built a framework to combine models trained differently. What was the goal, and what did they try?
Model merging aims to combine the strengths of different models, maybe models trained on different data or from different stages of training. The idea is the merged model might inherit the best bits of all of them. They tried a few strategies. Linear merging, also called model soups, basically just averaging the weights. They tried ties merging, which is more complex and tries to handle conflicts between models. And model stock, which involves picking and combining specific layers or parts of layers.
And what worked best for BIELIK?
According to the report, the simple linear merging, just averaging the weights, equally gave the best results on the Polish benchmarks. Specifically, merging 3 models from different points in the DPOP training worked well. They also tried adding the original pre-trained base model into the mix, and they used merging earlier too during SFT to consolidate improvements before doing the RLHF part.
Interesting, that simple averaging one out. Finally, for post-training, they used layerwise model quality monitoring with a tool called Weight Watcher. What's that about?
Weight Watcher is pretty cool. It's an open source tool that analyzes the internal quality of neural networks by looking at the statistical properties, the spectrum of their weight matrices. And it does this without needing training or test data. It uses some theory about heavy-tailed self-regularization. One key metric is the power law exponent, alpha. For well-trained layers, alpha is usually between 2 and 6. Lower alpha values generally mean better generalization for that layer. So the BIELIK team ran Weight Watcher on every checkpoint during DPOP training. This let them track how alpha evolved layer by layer. They could spot potentially over- or under-trained layers. This info helped them decide whether to adjust training and which checkpoints were most promising for merging or final use. Figure 6 shows some example plots from Weight Watcher histograms, flowcharts that visualize these properties.
A fascinating way to peek inside the model during training. Okay, let's shift to practicalities. Deployment. The report covers quantization. What is quantization for language models, and why is it important?
Quantization is basically reducing the numerical precision used to store the model's weights and activations. Instead of using, say, 16-bit or 32-bit floating point numbers, you convert them to lower precision, like 8-bit integers, or even less. This has big benefits. First, it drastically shrinks the model's size and memory. Easier to store, load. Second, it can speed up inference because calculations with lower precision are faster. This is crucial for running big models on hardware with limited resources. But there can be a trade-off with output quality.
And the BIELIK team offers quite a few quantized versions: GDUF, GPTQ, HQQ, AWQ, EXL2, MLX, Quanto, FP8, INT8. That's a lot of options.
Yeah, they really went the extra mile to provide quantized versions in many popular formats. This helps compatibility across different hardware and software setups, especially for people with less powerful machines. But, as the report warns, lower precision can sometimes lead to a noticeable drop in the quality of the model's responses compared to the full precision original. How much quality you lose depends on the method and how aggressively you quantize.
But it sounds like they tried to minimize this quality loss, especially for the GGUF versions. They used a two-step optimization.
They did. For GGUF, they have a specific two-step process to preserve quality. First is post-training calibration using an importance matrix. This matrix estimates how much different parts of the model's activations contribute to the output, based on a Polish-English calibration dataset. During quantization, the parts deemed more important by this matrix are kept at higher precision.
Okay, prioritize important parts. What's step 2?
Step 2 is, while most weights get quantized, the embedding layers, which handle the input words, and the final output projection layer, which generates the word probabilities, are kept in higher FP16 precision. This helps maintain the richness of the input and output, reducing the quality loss you often see with heavy quantization. They say this strategy lets the GGUF models run well on constrained devices with minimal quality degradation.
A very thoughtful approach to balancing efficiency and quality. Now, the critical part, evaluation. They did a massive evaluation across tons of benchmarks. What was the overall strategy here?
It was extremely comprehensive. They wanted to see how BIELIK stacked up against, well, everyone. Top models of all sizes, models of similar size around 11B parameters, and other models specifically built for Polish. The tables in the report only show a subset. The full results are on the public leaderboards. They used a wide range of benchmarks: OpenPL LLM Leaderboard, Polish MT Bench, Polish EQ Bench, CP Key for complex understanding, the Polish Medical Leaderboard, PLCC for cultural competency, LMZZ using school exams, and also broader European benchmarks like the European LLM Leaderboard, EuroEval, Open LLV 1v2, Mix of All, Berkeley Function Calling, Flores 200 for translation, Ben Checkmark for Czech, and even a Portuguese benchmark. They really covered their bases. They also note that BIELIK v2.5 instruct was just coming out as they were with the report, so full results for that latest version weren't available everywhere yet.
Let's start with the OpenPL LLM Leaderboard, focused on Polish NLP tasks. What were the key results there?
On the OpenPL LLM Leaderboard, the base BIELIK 11B v2 model got a strong average score of 58.14. That was competitive with much larger models and a huge leap from their earlier BIELIK 7B v0.1, which scored 34.34. But the instruction-tuned versions did even better. BIELIK 11B v2.3 instruct hit 65.71, which actually beat some really big models, including Metalama 370B instruct at 64.45.
Wow, beating a 70B model.
Yeah. Key takeaways were the whole v2.x family performed strongly, v2.3 instruct was the flagship, v2.5 showed promise, especially in function calling, and the parameter efficiency was striking, often outperforming models 2x to 6x larger. Huge improvement from the v1 series.
What about the quantized versions on this Polish benchmark? You said they held up well.
Remarkably well. BIELIK 11B v2.3 instruct was incredibly resilient. The 280 version, 8-bit integer, actually scored slightly higher than the full precision model, 65.76 versus 65.71.
Higher. That's unusual.
It can happen sometimes with quantization. Even more aggressive methods kept over 98% of the performance. Extreme versions like IQ2XXS still got 93% of the original score and beat older BIELIK versions. This really matters for deployment on regular hardware. They highlighted the Q4KMM version as a great balance of size reduction and performance.
Very encouraging for accessibility. Next, Polish MT Bench, testing conversational Polish skills. How did BIELIK do?
On Polish MT Bench, which uses multi-turn conversations, BIELIK 11B v2.3 instruct scored a top-tier 8.56. That matched the much larger Mistral small instruct 2409 and beat both the 405B and 70B parameter versions of Metalama 3.1.
Again, punching above its weight class.
Absolutely. Showed particular strength in math, reasoning, and writing tasks within the benchmark. It significantly outperformed other Polish models too, and you can see clear improvement across the v2 iterations.
Consistently efficient. What about the Polish EQ bench, measuring emotional intelligence in Polish?
On the Polish EQ bench, v2.3 instruct got an exceptional 70.86. That beat models like Wizard LM 2/8x22B and was close to the much larger Qwen 2.532B instruct. And the newer v2.5 instruct pushed that even higher to 72.00, surpassing giants like Qwen 272B instruct and Metalama 370B instruct. It also clearly outperformed most other Polish models here, showing a strong grasp of emotional nuance in Polish.
So it gets the mechanics and the feelings in Polish. Then there's the complex Polish text understanding benchmark, CP22. What's that about, and how did BIELIK fare?
CP2 tests understanding implied meanings, nuances, tricky questions in Polish. BIELIK did well here too. v2.3 instruct scored 3.63, putting it ahead of models like Mistral 8x22B instruct. It showed strength in sentiment analysis and general language understanding within CP2. V2.5 also looked good here, and overall BIELIK models beat 5.4 and the PLE and Polish models.
Seems like it handles subtlety well. Moving to the Polish medical leaderboard, how is its medical knowledge in Polish?
On the Polish medical leaderboard, using board exam questions, V2.3 Instruct scored 43.26%, and V2.5 improved that to 44.85%. Now, these aren't top scores compared to huge medically focused models, but it's respectable medical reasoning for a general model, especially given no specific medical pre-training. It beat Metalama 3.18B Instruct and Mistral Nemo Instruct, suggesting good cross-domain generalization.
Impressive for a generalist model. How about the Polish Linguistic and Cultural Competency Benchmark, PLCC? How culturally aware is it?
On PLCC, testing knowledge of Polish culture, history, geography, BIELIK 11B V2.2 Instruct got a remarkable 63.00% average score. It was slightly behind a couple of larger models but beat many others. This shows solid Polish cultural grounding despite its size. Again, efficiency was key. It was competitive with other Polish models, strong on history geography, and showed big gains from V1 to V2.
That speaks well of its Polish training data. The report also covers LLM ZISA using Polish national school exams. Performance there.
On LLM ZISA, LLMs behind the school desk, using Polish exam questions, BIELIK performed strongly. V2.1 Instruct got the best score in the family at 57.52. Performance was consistent across the V2.X series, much better than V1, and significantly outperformed other Polish models like Kira and Troll. Its performance was comparable to much larger models, highlighting that parameter efficiency again. It showed a good grasp of Polish educational material.
Strong academically, too. Then the European LLM leaderboard, how to do multilingually, especially on Polish, within that context?
On the European LLM leaderboard, BIELIK 11B V2.3 Instruct was strong specifically on Polish, ranking third overall among all models tested on the Polish subset, with an average score of 0.66. It showed balanced performance across tricky tasks like RSE reasoning, GSM-8K, math, HelloSwag, common sense, truthful QA, and MMLU, multitask understanding. The appendix also mentions its capabilities in German and Czech. And on the Flores 200 translation benchmark, it was strong, especially translating into Polish, and excellent from English to Polish.
Good to see its Polish focus didn't kill its other language skills. Lastly, the EuroEval leaderboard, a broad European standard. Key takeaways.
On EuroEval, V2.3 Instruct achieved a solid overall rank of 2.22. But again, its performance on Polish within EuroEval was exceptional, scoring 1.41, beating many larger multilingual models specifically on Polish tasks. The report also mentions decent performance across other Slavic languages in EuroEval Czech, Slovak, Russian, Ukrainian, etc., which makes sense given its Polish focus.
It definitely sounds like BIELIK 11B V2 is a major step forward for Polish language processing, consistently performing at a high level, often very efficiently compared to larger models. So to wrap up our deep dive, can you summarize the main achievements here?
Okay, summarizing BIELIK 11B V2 is really a state-of-the-art model for Polish. Its standout feature is parameter efficiency. It frequently matches or beats models much larger than its 11 billion parameters. It delivers strong results across a huge range of Polish benchmarks, general language, culture, medicine, education. And it does this while keeping good cross-lingual skills. The technical innovations, weighted instruction cross-entropy loss, ISIL, and adaptive learning rate, ALR, clearly paid off. Plus, the wide variety of quantization options makes it genuinely practical for deployment.
Truly impressive performance against the giants, really pushing the boundaries for Polish AI. So as we finish, here's something for you, the listener, to think about. Given BIELIK's efficiency and top-tier Polish performance, what does this mean for bringing advanced NLP to other, less represented languages? Could the approaches used here, like depth upscaling, WISEL, ALR, help create powerful, specialized models for other languages without needing absolutely massive resources? It's certainly something to ponder as this field keeps evolving.